Okay, so to start with the molecular characteristics of a sarcomere, I'm gonna draw one. So, this right here is gonna represent our Z disk. And then these little B shapes that make up the Z disk. It's made up of cal Z protein and alpha actin units right here. And then coming off of these, we have um, thick filaments, which I'm using red. I'll kind of draw out what those thick filaments are later, but they come out here into the middle. These little golf club looking things that we'll talk about later. Filaments, Jim marking green. I'm trying to make them look. Okay. So right here we call our Z disk. Repeating units of this form our Z disk of that way down. This area right here is called the A band. And this area right here and right here called I light band. And that's the A dark band. So I want to zoom in on the thick filaments first, which is, stay with the red. So the thick filaments, we have this protein right here, and wrapped around it are six heavy chains of myosin. Two are heavy chains, which look like these golf clubs. And then use this color orange to represent the light chains, and there's four of them. There's two heavy and two light. Alright, there's two alkyl. Alkyl chains, and these are used to support the head. And there's two light chains. These are used to support the entire molecule. I guess the entire compound. So myosin play an important role. We talked later about muscle contraction, but these heads can come into two different positions. We'll keep using red. So it can either be like this in the uncocked position, or it can be in this position, higher energy, cocked position. So going between these two different positions will be important when we start talking about the power stroke and all of that aspect. So we're going to touch back onto the light chain and all of its different components. We're going to have to switch around some of the colors a little bit just because there's a lot of different myofilaments. Okay, so our light chain is two strands of F-actin, fibrous actin. Around a copium called nebulin. Draw a nebulin like that. And these little circles stretched in a line. Like that these two are F actin. I'm trying to draw them so then they're laced around that molecule. So our F actin is this entire strand, but the individual strands of F actin are made up of G actin subunits. And I like to use the analogy of, at least the book uses the analogy of the G actin are these individual pearls, and then the F actin would be the entire strand as a whole, like a strand of pearls. So this, use a different color. Some blue covering this F actin. We have what's called tropomyosin. And in red, we're going to draw this Mickey Mouse looking thing, which we're going to call troponin. And troponin is made up of 3 different subunits. So there's troponin I, troponin T, and troponin C. So troponin I has a high affinity for F actin. So it's bonded, and I try to draw it in this molecule, but or in this diagram, I guess cartoon, but it's connected at, bound to the F actin. There's troponin T, which I tried drawing right there, has a high affinity for tropomyosin. There's troponin C, it has 4 compartments or 4 slots to be able to fill in calcium. That's what troponin C has, a high affinity for calcium. And then 2 of them are at what we like to call like the high state, and then 2 at the low state. At the high state, these are always filled with 2 calcium ions. In the low state, if we're at rest, then they're empty. But if they're filled, then we're at a higher state. And it's interaction of troponin and what it's able to do when it's filled that gets what we call the power stroke, which I'm going to be outlining next. Actually, no. I'm going to show the mechanism of ATP, how we get calcium into the sarcoplasm. So this entire complex of the sarcomere that we drew earlier, that's inside of what's called the sarcoplasm. It's the cytoplasm of a muscle cell. So, yeah, with the troponin C, if the low energy state or the low compartment is filled, then what that would do is it'll move tropomyosin. Because tropomyosin there's these individual myosin binding sites that are on the F actin, and the tropomyosin will cover that, so then we're not getting power strokes when we don't want them, or muscle contraction when we don't want them. And what troponin C will do is that when it's filled, it'll cause a conformational shift that will pull the tropomyosin out of the way so that the myosin head can be able to latch on and go into that myosin binding site on the F actin strand, and that will be partly the mechanism of how we get power strokes. But power strokes will lead to muscle contractions. Before that, I want to draw out what it looks like to be able to get our action potential and get calcium actually into the sarcoplasm, because the lower energy compartment of the troponin will never get filled unless we get calcium up there. So first I'm going to draw a little brain. Draw spinal cord. So we have a neuron that goes through. It'll synapse with an upper motor neuron, which will then synapse to a lower motor neuron, which will synapse onto our individual muscle fibers. This right here would be called the alpha neuron. And this entire unit together we call the motor neuron unit. So between each of these little areas, we call this the neuromuscular junction. And that is what we're going to zoom in on to be able to demonstrate and show what happens on a sarcometer level. So zooming in on that, I'm going to draw like a little mushroom-shaped dendrite. Like that. And we're going to draw our muscle fiber. Right here. And what we're going to represent is that an action potential will go down this neuron. It'll cause a voltage-gated calcium channel to open. Calcium will enter the cell and tell SNAP proteins to move vesicles and perform exocytosis, which release neurotransmitters into this neuromuscular junction. These neurotransmitters, which are acetylcholine, will then bind to an N1 receptor right here, which will cause a conformational shift. It's a ligand-gated receptor. So when acetylcholine binds to this N1 receptor, it'll open it, and it can let in either sodium or potassium, but due to the high driving force of sodium, typically we'll see sodium enter into the cell. And if we want to stop this signal, we have acetylcholine ACE. This is an enzyme that will break that up, so then we stop having sodium enter into the cell. This will cause a sphere of influence or Blanc. That'll cause this sodium voltage channel to open. So we'll get sodium come out of here. And then we have this vagination of the muscle fiber called a T-tubule. This is important because skeletal muscles, they don't receive their calcium from the ECF. They receive it from the SCR, which in other cells is called the smooth endoplasmic reticulum, but inside of muscle cells, it's called the sarcoplasmic endoreticulum, which I'm going to draw right here. So this is our SER. And then bound to this, we have two different channels that are going to play an important role. I'm going to define them right here. So down this T-tubule has a very small diameter. So it has these leak channels for sodium and potassium, which will cause depolarizations within this T-tubule. If those become too great, then there's this voltage chloride channel that to be able to return the cell back to RPM, it'll open, so then chloride can be able to leave the cell and then um, keep the RPM at a normal rate. But when this goes down, there's a sensitive L type V-gated calcium channel, called DHP, and it's physically bound to the RYR. It's called ryokinine, which is crucial for calcium to come out and into the sarcoplasm. So when this depolarization event comes down, it'll cause a conformational shift of this compound, or of this channel. So this won't open, but it causes a shift that will cause this to open. What keeps this closed is a compound called questrin. So I like to think of this as like those little twist knob spray on sunscreen things. So when it's closed, you try pushing on the button and then the sunscreen comes out. But then if you're able to cause a conformational shift, this will cause questrin to unbind. And if it unbinds, then this will open and allow for our calcium to leak into the sarcoplasm, which then it can bind to the troponin C in its lower energy slots, and then that will allow for tropomyosin to move out of the way. So then the myosin head can bind with the F actin on its myosin binding site. And this does it in like a very quick burst. So to be able to maintain contractions, it comes out in a quick burst. And then on the SCR, we have these ATPase circuit pumps. And these are high energy, require high amounts of ATP to be able to operate. And they'll suck calcium back in the SCR. So then we can repeat the process when another signal is given down. To be able to maintain a contraction, then multiple signals have to be given. So next we're going to go into the mechanism of muscle contraction. So I'm going to draw 4 different little sarcomere diagrams to be able to demonstrate that. Use a different color. I'm going to use red this time. So here we just have a super simple diagram of our sarcomere. We have our myosin head, which at state will have ATP on the top, be uncocked, and then we have our phosphate right here. So to be able to bind the system, we had to add in calcium, like that. So when we add in calcium, then when we draw our sarcomere this go round, we have our ADP bound. Still, it's in the uncocked position in our phosphate. And then to be able to form what's called a power stroke, this formation of that bond will cause our ADP and our phosphorus to fall off. Which will give us this conformation. We go into the uncocked position. And then we introduce ATP into the system. So then we look like this. ATP on the head, still in the uncocked position. And then to be able to get back to our starting point, then we hydrolyze our ATP. Okay. So, with the mechanism of the muscle contraction with skeletal muscle, this area right here where we're removing our ATP and forming this bond, it releases a lot of heat and energy. We call this the power stroke, which is where the how you get muscle contractions. Like your actin will pull on the rest of the Z line, and then you're able to move the muscle however you need it. So if you want a muscle to be contracted or if you want it to be released, then you change the concentration of the calcium. You either remove it or you add it into the system, and then that will cause it to go through this whole period. So we're adding it, we go into the power stroke, and if we want to go back into what's called the relaxation stage, this is where our circuit pumps are working and taking calcium back into the sarcoplasmic endoreticulum via our circuit pumps. And we're able to go back into the unclocked position, get back into our original state. So what we can see is that ATP is very important when it comes to our muscle contractions. So there's a lot of different sources of where we can get our ATP from. So we'll draw out that, and then we'll go through some whatever conditions the body would be under, or the sarcomere would be under, of why it would choose a specific one. So it's always used first is cytolytic or ATP, which comes from just chilling in the cytosol, and it lasts for approximately 5 seconds. So not super helpful for helping you run a marathon. The next one that we can see is called, or it comes from creatine phosphate. So what will happen is be an enzyme that's found on the M line called creatine kinase. It's able to take the phosphate from the creatine with the creatine kinase enzyme found at the M line. We can take ADP, add in that inorganic phosphate that we stole from the creatine phosphate. It'll form our ATP. And this is a little bit more effective, but still not the best. It lasts about 10 seconds. Our next form of how we can get our ATP is via glycolysis. What we do is we send the liver to break off glycogen. The body will turn the glycogen into glucose. And then inside the cytosol, body is able to turn glucose into 4-ATP. But in this process, it takes 2 ATP, so really we just get a net of 2 ATP molecules. And this can last for about minutes. And then if we really want quite a bit of ATP, be able to power everything we want, then what we will use is aerobic respiration. We should be going through all the different steps, going from glycolysis, create a pyruvate to go into the citric acid cycle, and then down the electron transport chain to get approximately 38 ATP. And this will last for hours. So then under what conditions these are really nice when we're going through very short sprint actions, very quick actions, trying to fuel white fiber um, muscles, or if we're putting the body underneath um, anaerobic conditions, we would use these anaerobic conditions. We're just performing aerobic conditions that don't put the body into anaerobic state. Then we would use aerobic respiration. It'd be the most uh, effective, especially since you can power for hours. You can walk pretty far without getting tired. So, aerobic respiration is a very good way to utilize, be able to use ATP. Thanks. Okay, so for this one, we're going to be comparing skeletal muscle cell or skeletal muscle sarcomeres and smooth muscle sarcomeres. So first, skeletal muscle. Only get calcium via the sarcoplasmic endoreticulum, while smooth muscles can do both. Skeletal muscles are also voluntary movements, or typically voluntary movements. Smooth muscles are really just involuntary. I mean, it would suck if you had to think every single time that you had to breathe, tell your diaphragm to relax and everything else. Smooth muscle, we typically talk about, or when we're talking about smooth muscle, we're talking about organs, anything on the digestive tract, gastrointestinal tract. Uh, I mean, parts of the eye. Not all eye muscles are involuntary. But yeah, that's another difference. Um, Skeletal muscles are only able to contract 30% and are a lot quicker. It's a very quick burst of energy to be able to contract them and then go back and forth. With smooth muscles, it takes longer for the muscles to contract completely. They can contract 80% compared to that 30% with skeletal muscles. And um, with that contraction, they can be able to sustain being contracted for a lot longer without fatigue. They pretty much don't fatigue. If they did fatigue, then you'd be uh, released in nature at points in time where you would want to and embarrass yourself. And then how this it's able to do this is with smooth muscles, they'll go through two different stages of phasic versus tonic. Um, so with phasic, it's very similar to how we start out with a muscle cell. Is we have the sarcomere right here outlined, or one part of the Z line. And then we have actin right here, and then this little diagram right here is going to represent our myosin complex. So right now we have it in the uncocked position, or the cocked position. Right here, what we would be doing is we'd be introducing calcium. And by introducing calcium, it takes a couple extra steps to be able to go through this whole situation. So, by introducing calcium, we can do that a couple other ways. If we're doing it through the sarcoplasmic endoreticulum, what will happen is the calcium will be released just like it would with skeletal muscles. But then we have a G protein that can be activated through epinephrine, or no, not epinephrine, acetylcholine. and it will go in to produce IP3, which IP3 will produce camp, which will then tell the cell to release more, or the sarcoplasmic endoreticulum release more calcium. And when it does that, we have this molecule calmodulin, where it's a protein that when we introduce more calcium to it, becomes activated. So it goes from this inactivated state where it looks linear to this activated state by adding in calcium, 4 different calcium on it, because it can hold 2 in each of its ends. It can hold 4 total. And then what that will do is it'll take this enzyme, myosin-like chain kinase, or MLCK, and take it from an inactive state into an active state. And when it does that, it's able to go into this stage right here where we have in the red. So we get our myosin actin complex, and then by adding on this other phosphate, we also increase the affinity of the myosin binding to the actin. And then what we would do from here is we would be removing the phosphate and the ADP like we would with the skeletal muscle, going similar to the what's it called? The sliding chain mechanism. It's similar to that, but the difference is when it goes into here, remove that phosphate and ADP. We saw that other phosphate that was added on via the myosin-like chain kinase, and then we add onto that ATP. It has a higher affinity, so it's able to latch on a lot closer. And instead of it requiring more ATP to be able to go through this process, what we can do is once we add on those 2 ATP molecules and get into the cock position, as long as that phosphate group that was put on by the MLCK stays on, then we can be able to go through this cycle and stay contracted for a long period of time. And if we want to be able to go back into what our normal situation would be, we'd activate this phosphodiesterase. So when it has this phosphate on there, it's in its inactive state. That's why I kind of drew the mouth of the enzyme closed. But to remove that phosphate, we would activate or deactivate rho kinase, which will remove that phosphate, put it into the active stage. It'll remove that phosphate, and then when we add ATP into the system, it'll hydrolyze like it does with skeletal muscle hydrolysis, and then it'll go back into our starting position. If we're going to change this, I'm going to draw this in green to represent the tonic. So it's all the same up to here, but instead what we would be doing is we would add in our phosphodiesterase to be activated with our rho kinase. So its mouth is open, and what it'll do is it'll take off this phosphate group. So we lose PI. I drew that in green, but it's supposed to be blue. So we'll take it off, and then we're going to go into this stage. Instead of hydrolysis, what we get is what's called the latch stage. And in this latch stage, well, that's for the muscle to it takes a long time for it to be able to, once it's contracted, to become uncontracted, or to relax. I'm sorry. So we still have the relaxation stage, which would be right here. It would go down into that, but during the last stage, it would take a lot longer for it to relax completely. So we're able to see that it's just a better, I mean, not better, but it's able to maintain that contraction for longer. Like if we're trying to, like for instance, with like your external or internal anal sphincter, it follows this kind of more tonic stage. Tonic, we get a more sustained level of calcium, while with phasic, it's a burst. and they both have their own individual purposes, but we can be able to go from basic to tonic just by changing the ratio of MLCK to our this is MLCP myosin like chain um, phosphodiesterase. So yeah, just major difference between skeletal muscle and smooth muscle. I guess I don't want to forget. Smooth muscle comes into two different flavors. We have single unit and multiple unit. With the single unit, they move as a entire unit, while with the multi-unit complex, we're able to see that each individual cell will move by itself, um, and that its moving will it can be changed by a lot of different factors like hormonal levels and um, chemical signals and all that. Um, but yeah, this is pretty much the basis of smooth muscle. So yeah. Okay, so first, what we're going to be talking about are our different kind of muscle fibers. That doesn't work anymore. Oh, we have our brain. I'll call them. Yeah. Gamma neurons, which I'm gonna label in blue. Yeah. Sensory. Going to label in green. Gamma. So they come in three different flavors. Um, so yeah. So alpha. Alpha. I guess it's so with these different things we have two different chain receptors. So we have the nuclear chain receptor. It's just going to be a straight line like this. We call it type 2. Type 2 sensory um, receptor. Have nuclear bag receptor. So it's gonna look a little bit more like this. It's called a nuclear bag receptor because this one's all bundled up together. So it looks more like a bag, well, it looks more like a chain. And it's a type 1A. And these both are different kinds of sensory receptors, like I was saying earlier. But how they differ is type 1A. Sorry, they're both stretch receptors. Um, so with these stretch receptors, the type 2 will tell us we're stretched, and how long, what the duration that something's been stretched. Type 1A says that tells the muscle that we're stretching. So if I was moving my arm and I'm going out here, the entire time I'm moving down, my type 1A, 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 telling me that we're stretching, and then right here, type 2 would kick in and say, okay, if we're stretched right here, and then say, okay, still stretching, type 2, type 2, type 2, type 2. Okay. So there's those two different types of receptors. And then up here on top, this is a poorly drawn cross section of vertebrae. Okay. So this vertebrae, this is going to represent our alpha neuron. That one right here is going to be our inhibitory. Or yes, our other neuron. So following, there's a green line. This is going to represent our stretch reflex pathway. So with our stretch reflex pathway, let's say this is to an alpha neuron telling our what's it called? We're doing that the knee-jerk test that you do at the doctor's office. And that green line is going to be telling, so we'd have that EPS here and excitatory postsynaptic potential right here. And what it's telling us is that we're going to be contracting that muscle, or yeah, be sending a signal to be able to stretch out our quadriceps. And then say this one is with our keeping blue hamstring. So what our stretch reflex will do is that it'll go down this signal, and then because a signal can't be both inhibitory and excitatory in the same neuron, so then we'll go around, cause an EPS over here, which will tell this synapse, hey, inhibit the hamstring, so then when we're stretching your quad, our hamstring is being inhibited so it doesn't, or inhibited so it'll contract, so then we can stretch and lengthen our quadriceps. So that's the stretch reflex pathway. In the blue, we have the what's called the Golgi tendon reflex. So we know that our muscles are strong enough and have the potential to be able to, our tendons have the potential to rip off the bone that they're attaching. So what our Golgi tendon reflex does is it's able to tell the body to not overstretch. Will send an inhibitory signal, like we can see, or right here would be an excitatory signal with the Golgi pathway. And it would say to the hamstring to relax, so then we don't tear the bone away with the tendon. You can see it when, if you're curling, you're doing like a max, you'll feel your bicep kind of give way, and that's your Golgi and activating, and it'll cause your arm to relax down, so then you don't tear your bicep. So yeah, those are all our different types of muscle fibers with the what's it called? Stretch pathway. Those two are related to each other. The other one that we have is called the withdrawal pathway. So, withdrawal pathway, we have to bring up a new term called nociceptors. The reflex. Oh, and then another thing with the Golgi tendon. Sometimes you hear those stories of like the moms being able to lift up cars and that kind of thing. Um, the central nervous system, because typically with the motor neurons, it's these are like involuntary movements. Like if you're slipping on ice and your legs will be able to catch you, that's all being controlled via your spinal cord. So you're not actively thinking about it. Otherwise, you would cause a groin injury if you had to think about it. If you were too slow to think about catching yourself. So um, sometimes the Golgi pathway can be overridden by the central nervous system to be able to lift up cars or be able to catch yourself or those crazy survival stories that you hear. Um, that's achieved by the central nervous system overriding Golgi reflex, but that never causes the person not to be unscathed. They usually have severe damage, like if they were able to lift up a car to get like their child out from underneath, they probably tear all the muscles of their chest and all that. So the reflex pathway, we have a receptor, which will lead to a afferent pathway. To go to the afferent pathway to effector. So we first go from a receptor. With that, it's going to be a nociceptor. So these pick up and sense pain. They do this with depolarizations that lead to action potentials back into the polar phase. Depolarizations, which will cause you to be able to be affected. So, like, say you put your hand over a fire, your sensory signal would say, "Hey, you should move your hand." Goes up to our spinal cord. Spinal cord says, "Okay, move." And then you move away from the fire so you don't burn yourself. It's usually a very quick pathway. So that is the withdrawal. We have some kind of substance that's causing like a burn or pain or where the body perceives and registers damage, then the withdrawal reflex is to move away and out of that that signal. So yeah, those are our different pathways. Okay, so moving on, what we're going to be talking about is taste and smell. Taste and smell both have chemoreceptors. So the receptors in found in both taste and smell um, react due to chemicals being received. So let's first talk about taste. There's 5 basic tastes that we all know of, or that we know of thus far. First one is sour. salt, bitter, sweet, sour, salt, bitter, sweet, and umami. Okay, so sour is picked up the presence of protons, hydrogen, yeah, protons. Salt by presence of sodium, bitter. They're called quinones. Quinines. Quinines. Sweet is through carbs, carbohydrates, usually glucose slash sucrose, and sweet stuff. And umami is picked up through glutamate. Okay. So how these things are picked up is that we have our tongue. See, that's our tongue. We have these little indentations, and underneath these, in these little indentations, we call papillae. Underneath these indentations, we have taste buds, which are our receptors. There's about 150 receptor cells in each taste bud, and the average person has about 125 cells per square inch of their tongue. And if you have more than that, you have what's called super taster. If you have less than that, then you're what's called a non-taster. So the general pathway of how this goes is the saliva will digest the compounds. These compounds will bind, lead from a chemical to electrical signal, and then the brain will pick that up. What's neat about taste is it doesn't do action potentials, it only does greater potentials. So with taste, you can get really close to threshold, but you'll never reach threshold. So I'm gonna draw out just some different, 3 different taste buds, receptors, and just how their pathway goes. So I'm gonna use to represent. Okay. So this is our taste receptor cell. This one's going to be salt. This one's going to be sour. And this one will be sweet, bitter. Okay. So with salt, we have what's called a cation leaky channel. This one is going to be a sodium cation leaky channel. So when we have the dissociation, like we eat something salty, we have the dissociation between sodium and other kind of salt that is present will happen. It will enter into this little cell. And then once this goes in, the rush of this positive charge inside of the cell due to the sodium coming in will cause for membrane depolarization, which will allow over here a soda voltage gated calcium channel to be right here. Calcium will go into the cell and cause snare and snap proteins to release neurotransmitters. Right here we have our neuron that is going back to the brain. And depending where we're at to the tongue, If I remember right, the facial nerve, cranial nerve 7, will do the anterior 2/3 of the tongue, or posterior 2, yeah, anterior 2/3 of the tongue. And then the neurotransmitter that is released into here will cause an action potential down, and the brain will perceive salt. These neurotransmitters are either ATP or serotonin. Okay, so sour receptor is very similar to the salt receptor. It uses the same channel, but this one is for hydrogen atoms. So hydrogen atoms will enter into the cell. This causes a rush of the positive to change. Here we have the smooth ER. The smooth ER here as well. So the rush of this positive charge will go into the cell, open, cause or a graded potential. Depolarization, yeah, a depolarization of the V calcium. This will calcium will go into the cell, cause our snare snap proteins, cell vesicles perform exocytosis, and then same thing onto the neuron. Now you look at these two and you're like, oh, that's very similar. Things that can change is the proportion of potentials received. Smell can have a big influence. Same. And then just other receptors can help the brain to be able to interpret between salt and sour. Other. Okay, so then with sweet, bitter, and umami, like it was earlier, carbs, the quinones, and then glutamate. These ones will have a G protein receptor, and the ligand will be, if it's a sweet, I mean, there's a specialized G protein receptor for each one of these different types of tastes. For sweet, the ligand would be the carb. For bitter, it'd be the quinone, and then for what's it called? For umami, it would be our glutamate. So when our ligand attaches, it'll cause for phospholipase 3 to allow for IP3 to come into the cell. IP3 will cause our SER to release calcium from the cell. As calcium is released, it'd be like the others, where we get our snare and our snap proteins to perform exocytosis and create an action potential that is unique to one of those taste bud receptors. Then moving on to smell, it's gonna be a little bit different. Um, erase, erase. So with smell, it's also a chemoreceptor. What will happen is that we'll have olfactory particles travel up into the nose. Right here, there's mucus that will trap all those different particles. Um, and then when those particles, well, mix into the air and the mucus layer, we have some receptors there within this mucus that are G protein receptors. Just to draw this. So that's their skull. Right here we have what's the ethmoid bone, and then between this ethmoid bone we have the cribriform foramina. Once those particles link with this G protein receptor, then what that will cause is that adenyl cyclase will create cyclase will create CAMP. Then CAMP will open up the trying to scroll up in cation channels. Cation channels, once they're open, will cause a depolarization event, which will lead to the opening of chloride channels. When those chloride channels open, that depolarizes the membrane and leads to an action potential. That is received directly through the cribriform foramina into the olfactory bulb, which should be located right around there. Just going over that again, particles go up into the cell. Mucus will be able to trap them. Those particles go attach to that G protein. That G protein will cause adenyl cyclase to form. What's it called? Form CAMP. CAMP will then open up cation channels and cause a depolarization event, which will open up chloride channels and lead to an action potential of those particles traveling up into olfactory bulb in the brain. So yeah. Switching gears, we're gonna go from taste and smell to hearing. So hearing is not a chemoreceptor with hearing. It's receptor. So when this receptor is moved, that's how it has it's able to move into action potentials because all of our senses are the product of different action potentials. So if we're gonna draw an ear, that's not an ear. So we're gonna go inside the ear. And then here we're gonna have this looking thing, which is our membrane. And that. Should that lead into something that looks like this? Okay, so going through this, we get our sound wave. Because that's how sound travels, is in waves, different air compressions. I'll go down this, which is what we call our external auditory meatus. And the sound travel wave will vibrate the tympanic membrane right here. I have a battery? Oh no, it's a base application matter. Tympanic membrane And what the tympanic membrane will do is we have the malleus, incus, stopes bones. And so these bones are, I try to draw them, but and how they're kind of what they look like. Not really. Um, they're matched up end to end. So as the signal goes down and the tympanic membrane, I had to draw these in proportion size. The tympanic membrane is much larger than these three ossicles. Um, so as they go down, the signal is amplified, and this little seashell-looking thing is called the cochlea. Where it's inside the cochlea that we have our individual hair cells, which is our mechanoreceptors. So with hair cells, they're all set to specific frequencies that when those are triggered, then you'll be able to perceive sound. So if we were to draw what the inside of the cochlea would look like, we'd see these maybe shorter hairs, and then it just goes longer, longer, all the way down until this point right here. The shorter hairs correlate with lower frequencies and deeper sounds. The longer hairs are higher frequencies, higher pitches. All right, other way around. The higher frequencies correlate with the shorter. Yeah, pretty sure. Yeah, with the shorter hairs, and then the higher frequencies with longer hairs. So with the hair cells, transferring the potassium as you go down into the channel. If we're going to draw it bigger, we have all these different leak channels that go further and further down until when it interacts with the hair cell, it'll cause a slight shift. Of the hair cell, it kind of looks like a comb looking thing. So when we have that shift, that's the perception of sound, is this will cause the membrane inside of the cochlea to go up and down. And wherever that is at, correlating with the hair cells, then we're able to tell and perceive what that pitch is. So yeah, that's hair cells for you. Okay, so we're gonna start by doing vision. So, starting with vision, we're gonna draw an eyeball. So, I can't do that weird. So with eyeball, we'll have light come in, our light's gonna represent orange. Okay. So with light, when it comes in, there's different structures that we're gonna want to go in. So travel in through the pupil, travel through the lens, and then through the lens, we'll go through this gel-like fluid area called hue. Here's fluid. And then once it hits the back of the eye, this is where we have photoreceptors. And with these photoreceptors, once they're struck with light, then we have some reactions that can lead to action potentials that are followed down this neuron, which we're going to call the optic tracts, which will travel up into the optic chiasma and then into the brain, where the vision will be interpreted in the occipital lobe. So when light goes in, first with these photoreceptors, so photoreceptors Perceive photons and transfer these into action potentials. And we'll draw out that mechanism just a little bit later. So yeah, light goes through. With our lens, the lens can go through this process called accommodation. So when we're going through accommodation, the lens can lengthen or shorten. Uh, due to um, what is it called? Filamary. Due to ligaments, and ciliary muscles. So if we were to draw the eye like this, we've got the uh, lens like this, kind of like a sound looking thing. Around here we have our ciliary muscles, and then we have these little ligaments coming off. Right. It's like a curtain apple. So these ciliary ligaments, when they contract, when the ciliary muscles contract, it'll cause tension to come onto the ligaments, and our lens become flatter. Okay, so because we're more concave, then we're bending less light, and that when we're oh, that happens when we're looking far away. So it's the complete opposite. So we invert everything. If our lens is going thicker and more football shaped rather than pancake shaped, and we're thickening the lens, then it's becoming more uh, convex, which means that we're bending more light, and we're looking at something closer up. As we age, we can get a condition called presbyopia, where if you're reading something super close for a long period of time, then typically what older uh, people will need uh, glasses to be able to put together words correctly. Um, and then when we're causing the lens to become more convex, more constricted, we're looking at things closer up, we can tire out those muscles. So a good exercise you can do, especially if you're reading a lot, is you can occasionally like look past further away to be able to give your eye muscles a break, so then you don't tire them out as much and develop vision impairments later on. Okay, so there's two different photoreceptors that. Erase those first. So there are two different photoreceptors with the eyes. There's rods and cones. So rods help us to see black and white. Cones, we can see red, blue, and green light. And then by combining activation through these different of the cones and the rods, we're able to see all the different shades of colors that are present to lives and situations, which is pretty cool. So if we're gonna zoom in on one of these photoreceptor cells, it looks something like this. Here is going to be our bipolar cell. This is our ganglia cell. So right here we have this compound, retinol, and when light has it hit into the back of the eye on the macule, the 11 retinol is in the cis position. 11 cis, right. Connected to this, we have a sodium channel that is held close due to cyclic GMP. And over here we have a voltage calcium channel. So what will happen when light comes in, it can cause a conformational shift of this to go from 11 cis to 11 trans. That'll cause cyclic GMP, or that'll cause cyclonucleic phosphodiesterase to become activated by activating this alpha 1 subunit. So when that becomes activated, it'll eat up and get rid of that cyclic GMP, which will open up the sodium channel, cause a depolarization event, which will cause our calcium channel to open, and then certain SAP proteins release glutamate into this part of the ganglia cell, where there is then a receptor that can either be our mUR6 receptor, or it could be AMPA receptor. Just kind of depends. So if more glutamate's being released in the AMPA receptor, then what will cause is another action potential, cause another sodium voltage gated channel to open, which will release more glutamate. And one of the rules that we can remember with vision is more glutamate being released only happens when dark is being received. So if more glutamate's released, then what the brain perceives is it's the absence of light, or it's dark. If there's less glutamate, then it says that it's light, and we can see that. Instead of these vesicles coming off and be able to come into here, there's going to be a compound that closes this channel and doesn't allow things to pass through it. So if nothing's passing through there, then we'll have the action potential, so there's less glutamate coming through here. A different action potential will come down and then activate a neuron and let us know that, oh, there is light. Then this is also a similar process with cones. That one is more with, I guess, cones and rods go through that sequence. Then we also have, what's it called? Optic fields. Optic fields. So we're going to draw these three separate things, or visual fields. Visual fields. So visual fields come in two flavors. We have on, center, off, surround. Then we have off, center, on, surround. So at the bottom here we have a neuron that's going through. We have our two surrounds. So if we're on, and then we have this other cell right here. So with our visual field, if it's on, center, off, surround, then that means that when light comes on, it will cause a response going. Oh, hi, Andy.
Sorry, I need to choose this one.
So if it's on, center, off, surround, then that will cause so with on, center, off, surround, on the second right here, we have on, center, off, surround is going to be AMPA, which would be right here, the secondary receptor. And then if it's off center, on surround, then we have UR6. So with a proportion of these different kind of vision fields as we have light coming in, and if it does cause a response, meaning on center, then it'll follow the whole little pathway, release glutamate into this area. And if this is AMPA, it'll bind, cause sodium to enter into the cell, and we can, which will cause depolarization, and then a voltage calcium channel will open, and then the calcium will cause exocytosis, then we get an action potential going down. But then on this opposite side, we have this inhibitory signal coming through with actually, no, we wouldn't, because we have off surround. So this wouldn't cause any action potential coming through, so we would not release GABA, which would inhibit this signal and say no light. And then it's the complete opposite for GluR6. If it's off center, on surround, then what will happen is when light comes onto these surround sites, then GABA is going to be released, inhibiting the GluR6, and then we get less glutamate coming, we get less glutamate coming through, and then I'm able to see, and then it's through these visual fields and different variations of on center, off surround, or on center, off surround, and proportions of the light is how we're able to see contrast of shapes and be able to see edges clearly is through those things. So you can kind of see in the video how there's that shadow right here. It's with the on center, off surround, and on center, off surround. On center, off surround, and off center, on surround. Different variations of that is we're able to see edges, shadows, and be able to have HD perception, vision. So it's pretty cool.